As industrial hygienists, we're interested in knowing what's in the air that people are breathing at work. To determine this concentration, we take a sample of a known volume of air. When an analyzing laboratory knows the sample volume, they're able to determine the concentration of the measured contaminant in the air in units such as milligrams per cubic meter. The volume that we collect is calculated based on calibration flow rates performed before and after sampling at specific ambient conditions, since volume is dependent upon pressure and temperature. But what if we calibrate under different pressure and temperature conditions than we sample? This is where the ideal gas law comes in. So, my name is Stephanie, and let's say that I'm a consultant based out of Virginia Beach. I calibrate my pump at sea level before taking a plane ride to Leadville, Colorado to perform air sampling at a smelter. When I return home, I perform my post-calibration, calculate the sample volume, and send my sample to the lab. Does it matter? In Virginia, I determined that I collected 400 liters of air at 1 atmosphere and 70 degrees Fahrenheit. But in Leadville, which has an elevation of 10,152 feet, or 3,094 meters, it was 9.81 psi and 45 degrees Fahrenheit. So how much air did I actually sample? We will use the ideal gas law to find out. The ideal gas law states that PV equals nRT, where P is pressure, V is volume, and T is temperature. N is the number of moles of the gas, which is constant, and R is the gas constant, which, coincidentally, is also constant. Since N and R are both constant, we can set our two conditions equal to one another. The first thing we need to address are our units. We have two different pressure units, and they need to be the same so that the units will cancel out in our equation. For pressure, we know that 1 atmosphere is the same as 14.7 psi, so that's an easy switch. With temperature, we must be in units of absolute temperature, so either Kelvin or Rankine. Rankine is your temperature in degrees Fahrenheit plus 460, so we'll go ahead and change those. But you could also use Kelvin if you were given the temperature in Celsius. Now that all of our variables are in the appropriate units, we'll rearrange the equation to solve for the volume of air collected in Leadville. From here, it's just plug and chug. So we set up our railroad tracks, insert our values, verify that all of our units cancel and that we'll be left with a volume in liters, and punch this into our calculator. And this gives us 571 liters. Since we actually collected more air, that means our real concentration is lower than what we thought. So in this situation, we may have recommended controls that were not necessary for the exposure levels at the facility if we hadn't calculated our actual air volume. Now, think about the consequences of calibrating in Leadville, but sampling in Virginia Beach. Thank you for watching.